Hi, I'm Elle, and welcome to my talk, Adapting Continuous Integration to Machine Learning. I'll start with a little bit about me. For the last decade, I've worked mostly in academic research in various areas of neuroscience, and one constant in my work is that I've always done a lot of mathematical modeling, and I really love getting to use big computers. So after I finished up my PhD last November from the University of Washington, I was interested in how scientists work, their methods, particularly the methods around managing increasingly complex workflows, and I joined Iterative, which is the team that makes DVC, or data version control, as a data scientist. So DVC, data version control, our flagship tool, is a tool that you might know from some of the MLOps space. It's a way of extending Git version control to things like data sets and models that are ordinarily kind of large and you wouldn't want to manage with Git. So that's kind of our, our flagship project. And today I'm going to talk about some new work that I've been involved with over the last few months on our, our latest project. So let's start with this figure that I love. It's from a case study from Microsoft. And the authors reported that teams, whether they were working on speech or search or ads, whatever, as long as it involved some aspect of machine learning, they tended to follow a very similar workflow on software projects that had some machine learning aspect to them. And of course, there's a lot of folks along this trajectory. They're not all data scientists. We've got data engineers, so people who specialize in collecting, cleaning, and labeling data. And then data scientists who typically would take that data set that's ready to go, and they would do featurizing, trying to understand the data a bit better, hypothesizing, building models. And then we've got folks whose specialty is the software and the engineering and creating systems and applications around models and then serving them, keeping them stable, all that good stuff. And this is an organization that is run by adorable baby animals, and that's great. That's exactly what we need right now. Anyway, everything is fine if this project proceeds linearly, going from data engineer hands off the data to the data scientist, who hands off their model to the software engineer, but of course, this never works. As you can see, the authors of this figure have drawn in these little arrows suggesting some recursion, and indeed, that is pretty standard. So there's a couple ways that this kind of linear flow breaks down. One is that really great machine learning models often take, quite a few iterations and feedback, and that feedback can come in the form of, maybe our data set is changing or something about the application is changing, or it could be that the system constraints are, quite particular, and data scientists have to work with that. So they get feedback from software engineers, and then they might have several iterations of discussing what the model will look like in production and feeding that input back into the data scientist's work. Also, data scientists need to be able to anticipate the constraints that software engineers will have, so they really need to be able to, to see or understand in some way if the dependencies of the project that they're developing locally will work in production. And everybody on the team needs to know where the data came from. And I'm so sorry that it looks like my head is cutting off the baby animal labels, but hopefully from context you can get it. So there's a lot of back and forth, a lot of circularity, and this can all get quite confusing and complex, and it becomes a thing to be managed in and of itself. But machine learning although it's new to the software engineering stack, we have, a lot of practices from software engineering that are great at dealing with complexity. And specifically, we can look to the field of DevOps for some inspiration. So DevOps is putting together developers and operations. So developers are people that want to develop cool features, they want to experiment, they want to make things fast, kind of like a data scientist can try out a bunch of different models. And then ops, people that need to keep the system stable and running with no interruption. So we can think of that as more of like our engineering guys and girls. So DevOps had a pretty big revolution, in the last decade or so. And it's now a mainstay of, most major tech companies that they have a lot of DevOps practices. But machine learning, it's still, because it's new, we're still figuring out what is a team that works on a full stack machine learning project going to be like. There's not as many DevOps principles and standards that are, ingrained in the same way as in software development. But we're interested in seeing how well those ideas can extend. And in particular, we're really interested in this big idea of continuous integration and delivery, which I will explain. And we're going to abbreviate this CI/CD. So CI/CD is a practice that establishes collaboration rules between developers and operations specialists. And it's part philosophy and part practice. So let's take a look at what that means. Let's get, a little less abstract. The idea is that you have a code base for your project. And whenever there's a change in your source code, a build will happen automatically. And then some tests get run on that build. And if the build passes the test, then the modified source code becomes a candidate to be merged into the main branch of your project. And if you fail, then you can keep iterating on this. And you might be able to tell from the way I'm talking that this is often done with Git, that we take out a branch, a new branch to try out some new features. And when we push that branch, when we make this pull request to our central, our CI server, then we will be getting the tests run, and then if everything goes well, then we can merge the branch into the main part of the project. And so we're using a Git flow where the main branch is presumably what will go to production, and we use branches to experiment. So the idea here is that actions like Git commits and pushes will trigger feedback, and every round of feedback can produce a release candidate. Because we're always testing and because we're always preparing to release something, we're like, it's really fast to turn around something new. The idea is to get out of having to wait months and months to test something out because, to get it ready to go into production, because every day you're used to testing. So let's take a look at what's different when machine learning is part of your workflow. So a couple things. First of all, it's not enough to monitor changes. It's not enough to monitor changes in your code base anymore. You also have to monitor changes in your data set. So machine learning models they're sort of code and they're sort of data. They are a function, but they're not really that defined by their code. On a lot of applications, and particularly in deep learning, it seems like data is what really drives the result of what the model is like. So we have to monitor for changes in our data set, because if the training data changes, that's as good as changing your model. Another difference is that instead of building software, we're no longer compiling, we're training models. And even if we're training them, it's intensive sometimes. A lot of the computers that can run a standard build for software development are just not up to training a deep learning model, or even a quite large, linear model. If you've got to do a really big matrix decomposition, you don't always want to do that on the computers you have lying around. Sometimes you're going to need some hardware or just some special CUDA drivers. It's not trivial. Another difference is that when we run tests, we have we're actually evaluating the model. We're going to the way we evaluate it is not like these pass-fail kind of things. It's like, I just gave it some new data, some held out data, and I want to know how my new model performed. And we have to be kind of detailed and, investigative about it, because of just knowing a single score, like, okay, did my accuracy improve on the new model? is not really enough, because we may have in fact lost something, like we've reduced precision, and perhaps that's really not okay for our application. And so this kind of evaluation of, did my model get better, actually requires some domain knowledge, both about what, how data science works and about the problem that you're working on. So these are things that, do not really make sense to binarize into checks when we really want a more conclusive and detailed report about how the model performs. So why don't we have this yet? A few reasons. First of all, version control can't always track changes in data sets. So like I had talked about, a lot of this is very Git driven, it's very Git centric, and a lot of data sets are not things that you want to be keeping in your GitHub repository. Data sets are frequently on the, a bit too large for traditional version control, so we need a way to deal with that if they're going to be triggers as well as code changes. Next is that training models isn't like building software. So again, sometimes our CPUs that we have around are just not enough, and we need a little bit of extra power. And evaluating metrics is more complicated. All right, so what's next? This is where we come in. So the philosophy of my organization is that we build tools that are going to extend, practices from software engineering to ML. And in specific, here we're looking at how can we extend CI/CD practices from software engineering to ML. And we are tool makers. So we're kind of going to start here. I'll show you our tool, but first I'll show you kind of a wish list of these are the issues that we think are most important to solve. First of all, we have to have some kind of more advanced data management. We need to be able to version data like code. Next, we need our CI system to be able to allocate cloud resources to train models. So it has to be very flexible, because at this moment in time, there's a lot of different solutions for orchestrating the compute resources to do machine learning or deep learning. So we want to be able to have your CI system use whatever resources, likely in the cloud, but could be on premise, whatever. But, it needs to be flexible to use your compute resources. And we want to be able to provide feedback in the form of not checks, but metric reports, and even possibly data visualization or interesting samples from a trained model. Lots of possibilities here. So I'm going to show you now how we've been approaching this so far. The work that I'm going to show you is a collaboration with Dmitry Petrov. Dmitry is the DVC creator and CEO of our organization. David is a developer who's been working on this project with us from the beginning, and me, I'm a data scientist. Okay, so now that we know a little bit about what we want, I want to tell you how we're going to do it. So our team, we work on DVC. DVC is a way of extending Git version control to larger things like model files, data sets, big things that you don't want to stick into Git, but that are really critical for machine learning projects. So because we're in the Git ecosystem, our attention has been caught by a couple of developments in that world. We have GitHub Actions, which is a continuous integration system that is supported by GitHub. So it's basically anytime your GitHub repository detects a change, they will provision a computer for you, and you can run whatever workflow you want. It is really cool, and there's a neat marketplace of actions that you can check out. And there's also GitLab CI/CD. Again, my head is cutting this off, but GitLab CI is a wonderful suite. It's really, I think it's like one of their specialties. It's a beautiful CI system. So both of these, for the purposes that I'm going to talk about today, are interchangeable. We've developed the tool that I'm going to show you to work with both of them. And I'm going to kind of give the examples in the rest of this talk in GitHub because of it's completely free. So it's maybe a little bit easier for somebody who's totally new to this to get in, but everything I'm going to show you works fine on both of these, and there is no difference in what you can do in these systems as far as my talk is concerned. Okay. So here's our project name, Continuous Machine Learning. We have started an open source project about using continuous integration from these two systems, GitHub Actions and GitLab CI, and we're planning on expanding to some other common providers with machine learning. So continuous machine learning. And here's our beautiful logo. And there's two ways that you can follow our project. One of them is on the cml.dev website, and we spent a lot of time developing like use cases here. Okay. Oh, there we go. We spent some time developing use cases, so all different kind of projects that are ready to go out of the box that you can copy and paste to your own project and try making them for both GitHub and GitLab. And we've got a repo on GitHub that you can come in, open issues, make a pull request for a new feature. It's pretty active, and it's got tutorials, all that. Okay, so let's revisit this figure. So GitHub Actions, where does this fit in? I'm going to highlight it. It's this part. So what GitHub Actions does is that it can automate training and testing a model and then return the results to you in your pull request. And by default, this workflow, so whatever is your training job, can be run on runner machines provided by GitHub, but you can also use your own machines too. So CML works with GitHub Actions. So CML is not a new continuous integration system. It's kind of a library and a set of methods that you can use with either GitHub Actions or GitLab CI to help adapt those services to work with machine learning. Because right now, GitHub Actions is really designed mostly with software development in mind. But we think it's quite flexible, quite powerful, and can offer a lot here too. So I'm going to take us through how the priorities that we laid out earlier show up in CML. So first, let's talk about providing feedback in the form of metric reports. Okay, so let's say that we have a project in GitHub and we're going to use GitHub Actions to automate training and evaluating a model. So what we do is we create this special YAML file that's always going to be in the same file path. You just place it in this GitHub Workflows file. And this is the secret sauce for any GitHub action, no matter how simple or complicated. You create a YAML file here, and you're going to give it some, a couple of arguments in the YAML format, and then give it some instructions to run. And then whatever you say is what GitHub will do when it detects a change. So we have our file here. We're selecting some triggers. So for me, I'm saying my trigger is going to be push. When the repository detects a push, then this workflow is going to be run. I am specifying a Docker container here. So I'm pulling first the operating system for the runner, and that's for the machine that GitHub is provisioning for me, a runner managed by them. I'm pulling the Docker container for the CML project, but you can also use your own Docker container, or you can use no Docker container. And so when this happens, we're going to run the following workflow. We will install some requirements. We're going to run a Python train.py is my script. And then we're going to use some CML functions and a little bit of bash scripting here. It's fairly mundane stuff. And then we're going to use this to write a markdown file, report.markdown. And we're going to use CML to deliver that markdown file. And I'll show you what that means. Essentially, when you make a pull request, you get a report, and it appears as a comment in the pull request. So here you can see that we've got, we made a commit on this pull request, and we printed out the accuracy of the model that was trained by Python train.py, and we printed out a picture, and the picture is an ordinary PNG file. It's not special in any way. And so the value of having this appear in your pull request is that now this result from your model training is visible to your team. And when you decide if you want to merge this model into your, the main branch of your project, you have this available to you, and it's always linked to the commit that generated it. So hopefully when you have this, you and your team can have a more informed discussion and a conversation about whether or not this is merge-worthy. And let's take a closer look at what exactly is run in the workflow. We have a training script that outputs a text file of metrics and a confusion matrix. So the first thing we do is we do some bash scripting to take the contents of metrics.txt, put them in the markdown report. Then we're going to use this publish function that we've created here to take your confusion matrix PNG, host it somewhere, and put it in the report, and then we deliver the report with CML to your pull request. Okay, here's another example where I'm using DVC to make a table that compares model performance metrics from the last experiment with the master branch of the project. So DVC, you don't have to use CML with DVC, for the record. They are totally distinct. But because of DVC creates tools to do things like a diff for model performance across two different Git branches, I think it fits really naturally with CML and anything else that you're doing with Git flow. So if you're doing Git flow and data science, I think DVC is very natural, but I'm very biased here. This is my team. So here I'm using DVC metrics diff to create a table that says how the metrics on my current branch compares to what's on the main branch of the project. And I'm also using DVC plots to plot the difference in the loss functions. And FYI, DVC plots are just a wrapper for Vega Lite plots. So this would appear in your pull request. And here's another example using TensorBoard. So we wrote a helper function so that when you open the pull request, you'll get a link to your tensorboard.dev page where you can track your model training in real time. So if your model is training on these remote computers, you can still see it training on a TensorBoard. And there's a ton of flexibility here. You can pretty much put anything that can go in a GitHub Markdown document, so like anything that you could imagine putting on like the README of a project can go in one of these CML reports. So you could be making your plots using whatever visualization library you prefer. It could be Seaborn or ggplot, Vega, whatever. And likewise, any way of generating a table too. So this works with every programming language because of it's very high level and it's quite agnostic. So Python and R, even though I'm only showing you Python examples, it works quite well with R. Okay, so we've been exploring a couple of ways to use these reports, like in what situations do they provide the most value, and there's a couple cases that we've considered. So one, as in the example I showed you, is that you can use the report to tell you about how model training went on your remote machine. So it could be either to use it with TensorBoard to track model training in real time on a remote machine that was, if your training job was triggered by the continuous integration system, or it could be to simply return, some of this model evaluation, like what does the confusion matrix with my trained model look like, and it could be on your training data or on your validation data. I really like transparent, reproducible, and detailed test results. I think that, even though we're just at the beginning of what we can put in a report and thinking about it, I think that the real strength is coming up with really descriptive and interesting tests to put here. And one thing to note is that you don't have to train your model using the CI system. You can just train it locally and then check it into CI when you're ready. So only commit the model that you like the most, and then this could be a test suite. So you can do things that are akin to like a unit test on your model or your data set, and only report the results of that. So you don't have to be training in the CI system to get the value of testing. And finally, we can also look at reviewing data and models like code. So if we have ideas about like model metrics diffs or a data diff, if we are reviewing, on a pull request, maybe the data set has changed and, we want to make a diff to see how far has it drifted from where it is on the main branch. All of these things can be done, and we're still building and exploring use cases around it. So the idea here is that similar to how we might open up a pull request and as a team review code changes, we can also review data and models in this way. And kind of to build on this, we've been creating a YouTube channel where we've been taking these use cases and doing them, with code that we've made available, and just live coding them and making this available to see what things people respond to. And we've gotten, some really nice responses. So we've had this for, I think, like 6 or 8 weeks now, and we've gotten, almost 17,000 views by today. So people seem to be, quite interested in the approach of what can we use GitHub Actions for in automating my machine learning pipeline. And so, so like I said, we're still building up, cool applications for it. Okay, so the other priority that I wanted to talk about is versioning data like code. And in fact, this is what we have DVC for. So our other project, DVC, kind of was a precursor to CML because it had to be there. So DVC extends Git versioning to datasets and models, and here's a little bit about how it works. It has a Git-like syntax. So if I have a repository where I already have Git working, I can do DVC add on a data file, and I can push that file to remote storage. So I'm doing DVC add is going to put the file under DVC tracking, and DVC push will push my data, my CSV, into cloud storage. And on your local machine, DVC will create this lightweight metadata file. So it would create a data.dvc file that can be tracked with Git. So I'm showing you here a sample file, and it contains a hash that indexes the version of the data set as well as its location in cloud storage. So basically, you can treat data as code so it can be Git versioned even though the data set itself lives in cloud storage. But in GitHub, your GitHub repository, you will have a link to how that points to your data in cloud storage. And so we've created in CML an approach to let you use DVC in your GitHub Action. So you can just pass some credentials to your workflow, and then you can do things like DVC pull data, DVC repro, so reproduce a pipeline if the data set has changed. And then you can also use DVC to push results from your CI run. So if you created a new model on your CI run, you could use DVC push to push it into cloud storage. So pull data, what it's doing is it's going into the cloud, pulling the CSV, putting it on the runner. And then DVC push is going from the runner to the cloud. Okay, so some consequences for continuous integration here. First, changes in your dataset can now trigger a GitHub action, even if the dataset itself isn't part of Git. GitHub Actions can now push and pull very large artifacts to and from cloud storage, and data and model versions are linked to every model training run. And because of you can start using things like S3 storage, you can have these serverless storage methods. That means that you have one less server potentially in your workflow, and that's great. All right, our third priority is that we wanted to be able to let our CI system allocate cloud resources to train models. And really quickly, because this one is super cool, but it's actually, we're changing the approach right now. And so I don't want to over provide details on something that's going to change. But we've set up something right now with Docker machine that basically means that anytime you push, you will deploy cloud resources. So you can actually deploy an EC2 instance, and it will turn on and turn itself off after it's done running your job. And we're reworking this a bit right now with Terraform. It is super cool, but it's not ready today. But basically with this approach, in the way that we have it right now, we've done things like style transfer model on an EC2 instance that has a GPU. And the cool thing is, you don't have to worry about remembering to turn off your GPU or turning it on. The CI system turns it on and turns it off. Okay, so to be clear, there are many solutions out there, and a lot of the things that I've showed you are things that other teams have done. We're just trying to standardize it and make it into a cool open source project that kind of puts these resources together, polishes it, and try to popularize using CI systems like GitHub Actions or GitLab CI with machine learning. We really think that there's a big opportunity there, and we're hoping that, people, as they respond to this and try it out, kind of help us develop it. It's an open source project, and we love that kind of feedback. So just to summarize, what we've done here is we've created a couple approaches to version data like code, and that our approach was DVC. We wanted to let our CI system allocate cloud resources for training models, and we've been using this approach that's kind of using Docker machine in particular to deploy cloud resources from GitHub Actions so that you're not limited anymore by the compute that comes with the GitHub Actions CI system. You can use any machine you'd like. And we can provide feedback in the form of metric reports, and we have written this family of functions, CML reports, we've written a family of functions that will help you write CML reports in your pull request. And the priority here is making data science and DevOps more closely tied in the CI process. So We really like CI/CD because we think that makes a lot of sense for machine learning projects. It's a way of bringing together your training data, your source code, your modeling experiments all in one place. And that gives everybody on your team shared access to every version of the project, including its history and ongoing experiments, and it provides a standardized format for storing and sharing any kinds of files related to the projects, like data or models, whatever. And so I think it's cool because it's both a cultural and a technical shift. And, maybe the way that DevOps has been impactful for software development in general is something that we can also have in machine learning. Plus, automating things with really big computers is just a lot of fun. All right, thank you for listening. We are an open source project, and we would love it if anybody is interested in what we're doing, has a cool use case, wants to maybe come on a YouTube video with us, try something out. Maybe we can build something together. And we hope that you'll join us. So you can follow us on social media for project updates. We're always down for, check out the repository. And our video series is ongoing. So, subscribe, follow along, and hopefully it'll be interesting if you've liked this talk. All right, thank you, and I am happy to take some questions.